Our next presenter is Dr. Micheal Kattoura. Micheal is a materials research engineer at LSP Technologies, where he plays an integral role in LSPT's Materials Science Center of Excellence, which offers a wide variety of testing and measurement instrumentation to reveal strategies and benefits for improving metal components. Micheal received his PhD in Mechanical and Materials Engineering from the University of Cincinnati under the tutelage of Dr. Vijay Vasudevan, who will speak a little bit later in this presentation series. And I'm pleased to welcome my friend and colleague, Micheal Kattoura. Micheal, it's yours.
Thank you, David. Morning, good afternoon, and good evening, everyone. As David introduced me, my name is Micheal Kattoura. I'm a materials research engineer here at LSP Technologies. Today, I'll be talking about material properties enhancement of laser peening, and the main focus here is to dig into the technical basis for this enhancement. As David explained a bit about my background, I did my PhD at the University of Cincinnati under mentoring of Professor Vijay Vasudevan, and I joined LSP Technologies after I graduated, and I've been around here for around 4 years now. So, you guys are at a laser peening conference, so you're here for needing enhancement material properties, maybe looking for decreasing maintenance costs, or maybe increasing safety, and in most cases, a lot of the above and a bit more. So today in my talk, I will start with explaining what the materials team at LSP Technologies does, all the cool stuff we work on. Then I will move on and explain the basics for the laser peening process. I know a lot of people come from different backgrounds, so I wanted to have a kind of a same foundation for everyone moving forward. Then I will move to the core of this presentation, which is the material properties enhancement, and digging into the technical basis of how we're getting that material enhancement from laser peening. I will end with a quick closing notes and, of course, open the floor for your questions. So starting with the material group at LSP Technologies, as Jeff explained, we've been working on a lot of projects around the world, and one of the projects is delivering laser peening systems, as you can see here, to China, Germany, and again back to China, and moving forward, hopefully in Russia and other countries. The materials team responsibility when it comes to laser peening systems, to our Procuda 200 laser peening system, is ensuring the performance of that system, making sure all our systems are up to performance and meet all the requirements and are able to deliver the best laser peening performance from our processing. The second task that the materials research group does is, with all the new expansion of our projects and going to applications pushing the boundaries of laser peening, as Dominica explained and others will be explaining in the next few talks, the materials team responsibility is to work with our engineering groups to ensure we are supporting all the new innovation, all the new designs, and making sure all these new products that we're delivering actually meet their customer requirements and deliver the best laser peening process to these new applications. Here at Dublin, we have our application development and production cell. On the application development, and I'll explain a bit more about that process in the next slide, our duty is to interact with the customer, understand their problems, design laser peening solutions, and make sure to have proper processing to prove the benefits of laser peening. On the production side, once they're happy and they want to have production, our goal is to identify the process optimization and boundaries for the process. And from there on is to ensure the quality assurance that every part that we're processing meets the requirements needed. So briefly about our development program for new applications, and David Larman will be explaining and giving a lot of examples about this topic in his talk this afternoon at 4:25, titled The Path to Production. The process mainly starts with actually understanding what the problem is. Laser peening is not a broad processing technology, meaning we need to know where the problem in order to design a solution for that problem. That being said, that comes from learning as much as possible from the customer around the location of the failures, the type of the failures, the stresses, the environment being experienced by that component. From there on, we move to our modeling part. Stan Bovid, Director of the Materials Research, will have a talk around the modeling and all our work here at LSP Technologies. We use the modeling to optimize and tune down the number of parameters that we want to test to get the most optimum laser peening conditions for this part. From there on, it's more of a testing and verification. Testing can be done on samples or sample coupons, or you can do on a small set of parts. Once the confidence and the customer is happy with the results that they received, that's when we move to production. And at that point, as I said, is ensuring that we get the best processing for each of the parts being laser peened. So the final task that I want to talk about that the materials team does is research and development. We have a lot of topics that we investigate as materials team. The first one that I want to talk about is pushing the boundaries of the laser peening process. Laser peening process has, as Alan showed, they have been doing science around laser interaction with materials since the 60s and 70s and so on. But still, there's a lot of things to push that technology forward and to try to get the most out of it. And recently, Stan Bovid, again, Director of the Materials Research, recently published 2 papers that are linked to understanding and improving the boundaries of this laser peening process. The second type of research and development we do is developing physics-based, experimentally verified modeling capabilities. And Stan, tomorrow at 1 p.m. will be presenting more about this topic. The third research and development topic that we work on is new applications. Jeff explained a bit about additive manufacturing and other applications that he's excited about. Tomorrow at 2:30 p.m. Eastern Standard Time, I'll be giving an overview of laser peening for additive manufacturing. So these are a few of the highlights of the talks and the research and the work what the material team does here at LSP Technologies. So now moving to the part where I will give a brief introduction to the laser peening for the general audience. So in laser peening, as you guys know, we're using a pulsed laser that interacts with the surface of the material, and then that generates a plasma. We use a transparent overlay in order to confine that plasma. That transparent overlay is considered transparent since the laser passes through it without losing too much energy. While it confines the plasma, it pushes the energy from the plasma into the material, creating a shock wave. That shock wave is what generates the compressive residual stresses that I will be talking extensively about today. One optional overlay is the opaque overlay. Historically speaking, a lot of the applications were around titanium, and opaque overlays are used to prevent the plasma interaction with the material. And for titanium, that gives rise to alpha case, which is detrimental for the process. That being said, most of our processing no longer includes any opaque overlays except if it's for titanium. So now we have a plasma at the surface that created a shock wave. Well, the shock wave, when it propagates into the material, at the start you have the highest peak pressure, and that peak pressure needs to be higher than your dynamic yield strength, which is also called the Hignoid elastic limit. As long as your peak pressure is higher than the Hignoid elastic limit, your dynamic yield, you will be generating plastic deformation. Well, as the wave propagates into your material, it dampens, meaning you're losing the peak pressure. So as it goes into the material, it keeps going, that peak pressure keeps going lower and lower until you go below that ignite elastic limit, and then you'll no longer generate plastic deformations. So with that being said, now you're generating plastic deformation, and actually it's a gradient of a plastic deformation up to a specific depth of effect. So let's take that concept. We applied laser peening, we deformed the piece or part on the surface of the material up to a specific depth, and now we're putting that deformed area into the material. So we're pushing a plastically deformed material into the existing matrix. Natural reaction for the material surrounding it is to elastically respond, as in try to push back that deformation. And that's what gives rise to the elastic compressive residual stresses from the laser peening process. So now how can we control these compressive stresses? In laser peening, we have full control over the laser parameters, namely how much energy per each pulse that we generate. What's the duration for that pulse? And that's mainly measured in the form of full width half max of that pulse. The final parameter is what's the spot area, meaning what is the area of interaction of that laser on the specific material itself. All these parameters combine into one variable or one parameter that is called the power density. And in easy terms, the power density is how hard am I hitting the material. So the power density, and a lot of the research historically and even the recent ones by Stan, has shown that the power density is directly linked to that peak pressure, meaning the higher power density that you're using, the higher depth of residual stresses that you're achieving, and vice versa. So we have the ability to control what the residual stress profile that we need to have in order to get the best processing. So the power density is the main parameter that we control to process different types of processing materials. The second variable that we control, and here it's all either called layers or overlap or power density, pulse density, I'm sorry, denotes how many pulses or what's the formation of pulses or what configuration of pulses that we're placing on a surface. There's a lot of terminology among the different groups, and so I left a few options here. But with that being said, the main goal here is, generally speaking, the higher number of layers or higher number of pulses that you place on the surface, you will get added benefit on the depth of compressive stresses up to minimal returns kind of condition. With that being said, so now let's move to the core of this presentation. We're going to talk here about material properties enhancement from laser peening. And as I explained, the goal here is to give technical basis of how are we achieving these improvements. The first two questions that I usually get from any customer is, does laser peening work on my specific material or metal alloy? And for that, the answer is a simple yes. The main difference of laser peening different materials is what power density am I using. As I explained, higher strength material require us to use higher power density. As if it's higher strength, we need to hit it higher to get the compressive stresses into the material. The second question is a bit more tricky, is does it work on this specific part or this specific geometry or this specific feature? And LSP Technologies, as you can see in the short list here, we work on different parts every day. So we do have a long experience with working with different geometries, different parts. And we have the ability to, and I'll explain about it a bit in the next slide, to kind of design our laser peening process. And that comes from our ability to control our laser peening parameters as I showed them. So with that being said, we have the ability to model these laser peening, model the laser peening process of these components. So when a customer brings in any part that he is facing failures on or needs fatigue enhancement or life enhancement in general, we have the ability to take that 3D model and apply a laser peening process modeling on top of it. Again, Stan tomorrow at 1 p.m. is going to explain more about our ability to model different parts, and we can predict the residual stresses that comes out of the laser peening process, and we can estimate how much life improvement that comes from the laser peening process. Our modeling capabilities are supported by the large library of residual stress data that we have for different peening processes on different materials with different thicknesses and different geometries. So we have a large material database that our models can use to verify, build, and verify again until we reach a model that we're happy with, and then we can apply that specific model to a complicated geometry, which helps us optimize our laser peening process. And after that, it becomes, okay, experimental verification of the results that were generated by the model. So we do actual residual stress measurement to verify the simulation results. So I did show a bit of residual stress, and I didn't explain, okay, are these good? Are these bad? Historically speaking, as any other mechanical surface treatment, a lot of the original data is actually compared to shot peening. Shot peening being the most commonly used surface treatment in the industry. So historically speaking, again, and a lot of Alan's and Jeff's talks kind of touch based on that. Historically speaking, laser peening was used in applications where you're either doing laser peening in conjunction with shot peening, or in applications where shot peening is providing very shallow residual stresses, and you need that added benefit from the laser peening process. So in most of the applications, historically speaking, laser peening was used due to the higher depth of compressive stresses that you can generate. More recently, and because of the improvement in the technologies of the lasers themselves, we're able to reach much higher repetition rates. We're able to get much higher throughput from the process. That being said, now laser peening is actually being investigated as a replacement for shot peening. The goal is not to give higher depth of residual stresses, although we could. It is for all these long list of benefits that laser peening have over shot peening, namely controllability, no need for masking, and other characteristics that you can see in this slide. So now moving a bit into the actual material properties enhancement. And here is a short list of the most common metal enhancements that we mainly work on a regular basis. Most of the problems that a lot of our customers see are related to foreign object damage, similar to the first industrial application of laser peening. It's linked to fatigue life enhancement, fatigue strength, resistance to crack initiation and propagation. I will be explaining a bit about die life improvement, resistance to fretting, fatigue, and the last example is around stress corrosion, cracking, and all the new applications, and some of them are even old applications around that topic. So going back to this slide, this is what Alan actually presented, and what Jeff has the cool animation for that he walked through and explained. So the first industrial application for laser peening is on the F101 blades. And the problem here is virgin object damage, meaning something flies and hits the blade and creates kind of a notch feature. You can see that the blade performance before notching is here demonstrated as a pristine blade. The minute that you have a damage, you lose the majority of that life. And trying different types of shot peening was able to recover some of that life, but it's nowhere close to where the actual life of the pristine blade is. That's where laser peening was investigated, as you can see here. Even the notched blade was able to perform equivalent or even better than the pristine condition of the blade. So here is a video showing an example for laser peening our blades. Here at LSP Technologies, we benefit from offline programming. As you can see here, we do have programming capabilities to program the cell and make sure we have everything set up to reduce actual cell time. Here you can see a demonstration here, just a demo, for laser peening a blade in our cell. And you can see the intricate robot motion and in order to laser peen that leading edge of that blade. Okay, so let's get a bit technical now. So how does laser peening improve the fatigue life of components? And here I'm going to give a simple example from a rest hook. So the rest hook here is subjected to a bending stress. So you have the highest bending stress at the surface of the hook. And as you start going into the material, into the hook, because of the bending stresses, they start going down linearly. Two surface treatments were investigated here. You have laser peening and you have shot peening. So a very important aspect of how to quantify the benefit from a surface treatment that is generating compressive stresses is what's called a superimposition. It is, simply speaking, you have the tensile stresses being applied minus the compressive stresses that you're generating from the surface treatment. So using that concept, you can see the two lines. This one is for the shot peening, and this one is for the laser peening. And these are the actual stresses being experienced by the material. In shot peening, you are able to drop the magnitude at the surface, but because of the shallower depth, the material is still experiencing a stress level above 300 KSI, just below the surface. Whereas in the case of laser peening, the material is only subjected to a stress that is 200 KSI or even lower. So the total material, especially in that critical location where the failures are happening, is now experiencing a much lower stress magnitude than that of the shot peening. So what does that mean from fatigue life? And here mainly, let's focus on crack initiation phase. So in this graph here, you can see this is the baseline. Shot peening, because it dropped the magnitude at the surface and it lowered the magnitude in general, was able to get that benefit, and also pushing it from the surface to a lower subsurface location. In the case of laser peening, because the material was now only experiencing 200 megapascal or 200 KSI or lower, that's where the majority of that benefit and the fatigue life occurs. So long story short, the benefits from laser peening is generating compressive stresses that are counteracting the applied tensile stresses, so that the actual material is experiencing a lower amount of stress, net stress or total stress. A more common way of representing fatigue life data is through SN curves. You can see the same pattern of, okay, we're trying shot peening, we're trying laser peening, and they're giving better results. Laser peening is generating higher amount of improvement. And there's two ways of looking at these life improvements when you're looking at this SN curve. So you can take a fixed stress, let's say around 260 megapascal. You can see here the baseline is around 50,000 cycles. Shot peening is around, let's say, 100,000 cycles, and you have laser peening at around 300,000 cycles. So you can say in an amount of improvement at a specific stress level, shot peening doubled the life. Laser peening was able to generate around 6 times life. Another way of looking at it is you take a specific number of cycles. Let's look at the endurance limit, which in this case is 10,000 cycles. Looking at the endurance strength, you can see here the improvement generated by each one of these surface treatments. So the compressive stresses that we generated from the laser peening process or from the surface treatment again, is counteracting your applied tensile stresses, pushing your entire SN curve through lowering the actual experienced net stresses experienced by the material. So in the endurance limit is no longer down here at 180 or so. You're actually, the compressive stresses are counteracting that stress and pushing your endurance strength up to that 220 megapascal. This study that was also done on aluminum kind of separated the two aspects of fatigue life. They separated the fatigue crack initiation and the fatigue crack propagation aspects. So the majority of the life, as you guys can see in this graph, is from the crack initiation. Laser peening, the highest benefit that you get out of it is from the crack initiation. And looking at the same stress level that I gave as an example, you can see the baseline is around 50,000 cycles. Shot peening was able to push it at 100,000 cycles, whereas laser peening was able to push it 300,000 cycles. And the majority of that improvement lies in the ability to delay the crack initiation side of things. But also, if you guys focus on the crack propagation side of things, you can see the laser peening process was able to also delay crack propagation side of things. I know Mike Fitzpatrick has a talk tomorrow at 10:50 Eastern Standard Time in order to design laser peening patterns to delay that crack propagation. So in general, for industrial application and industrial parts, a lot of the parts that we receive kind of suffer from the same problems, which is kind of a feature with a high stress intensity factor. Examples are kind of notches, fillets, and holes. These high stress intensity factor locations are the weak points in that component. And by applying tensile stresses, that's how you're failing it and causing the fatigue crack to start and propagate. So as an example here from actual industrial part, again, as any component that we receive that has whatever geometry, we use our ability to model the part and generate programs that can process the part before even it going into the cell. That allows us to design programs and reduces the downtime for the cell. Here in this application, we're looking at a crankshaft. Crankshafts have both. You have holes in them for the oil, and you also have fillets between the different features. In this specific video, you can see that we're laser peening the hole feature. In order to improve the full life of the components, you need to laser peen and improve the life for the most critical components and the areas with the highest stress factors. And in this example, it's a combination of laser peening the fillets and laser peening the holes. Okay, so let's go back a step back. I did explain the improvement that we got from the virgin object damage, but I didn't explain how did we get that improvement. In a simple way of looking at it, virgin object damage is nothing more than notching your blade. So what does a notch do is actually it's a location of high stress intensity factor. So it's the weak point where a lot of the cracks are going to initiate and propagate. The fact that we're generating compressive stresses that again delays crack initiation, as I showed in the previous example, and both crack initiation and crack propagation. This is how the first application of laser peening was able to get the life improvement for these blades. So again, in simple way of looking at it, a virgin object damage is a notch high stress intensity factor location that goes through a crack initiation and propagation. And that's how laser peening, by generating compressive stresses, can delay crack initiation and crack propagation, improving the total life of any component. On the same theme of fatigue life enhancement, a regular component that we do laser peen on is the Pilger dies. These Pilger dies are mainly experiencing mechanical stresses. And a study with Sandvik has previously shown that laser peening was able to improve the life of these dies by around 3 times. Looking a bit deeper into this application, the majority of the failures and the highest location for stresses are actually in that groove where your crack initiates and propagates. In a similar concept, laser peening of dies, which are very high strength material, generates really high compressive stresses. These high compressive stresses are actually counteracting the stresses experienced by these dies, improving their life by 3 times. Something that is worth noting here, the best benefit is not just the fatigue life from these dies, but actually the fact that if one of these dies fail, you have to restack the entire rack of dies, meaning they have to take everything out and then reassemble, which puts a lot of maintenance time and downtime for processing. So for this application, although we improved the die life 3 times, the highest benefit and the highest interest from the customer was reducing that maintenance cost. Another investigation that we recently conducted with NATCA, NATCA is the North American Die Casting Association, is around die casting. So we did a study on die casting dies, and tomorrow at 11:40 Eastern Standard Time, James from Case Western, where these testing were conducted, will be presenting thermal mechanical fatigue testing of laser peen die casting dies. So in the die casting industry, it's not just mechanical, it's thermal combined with mechanical stresses that are being experienced by these dies. The final type of fatigue that I want to talk about today is fretting fatigue. And Alan explained that the first actual mechanical testing results and benefits of laser peening was around fretting. And here, fretting actually occurs, as you guys know, when you have reciprocating frictional contact. So you have 2 things rubbing on each other, creating frictional stresses and creating a crack initiation, which propagates at the later time. In a very similar manner, you're creating compressive stresses by laser peening. These compressive stresses counteract the applied tensile stresses from this fretting fatigue. And you can see that laser peening is able to generate a life improvement up to 10 times. But moreover, because you're generating compressive stresses, you're generating an area in this curve that failure is no longer generated. It's kind of a knee curve, similar to a lot of the SN curves for different materials. The reasoning here is below a specific stress, the compressive stresses that you're generating can fully protect the material from a crack initiation in the first place, giving the part almost a full life without failures up to the testing endurance limit. Now moving away from fatigue and talking about a very common metal failure that we work on is stress corrosion cracking. And in order to get stress corrosion cracking, you have 3 factors that need to occur at the same time. You need high tensile stresses, you need corrosive environment, and you need a susceptible material. So let's talk about this example here. So a common way of testing stress corrosion cracking is using a C rings or a U bends. And in this specific example, we have susceptible material, which is 300M steel. And we're placing it in a corrosive environment, which is sodium chloride. And we're applying tensile stresses, 1240 megapascal stress. So we have all 3 conditions to cause stress corrosion cracking in this part. So again, like a lot of the original data, laser peening and shot peening were investigated to improve the life of the baseline here. In this case, is as machined. You can see the as machined condition, the life from these testing was around 200 hours. Shot peening was able to generate an improvement and pushing the life of that sample up to 400 hours. Laser peening was able to run up to a 15 1,500 hours without failures. So the testing was stopped after 1,500 hours and no failures were detected. So now let's think, how did laser peening get that benefit? So going back to the basics, tensile stresses. Laser peening was able to generate high compressive tensile stresses and to a depth that you're protecting the surface and the subsurface, which is the most susceptible areas here in this component. When you're countering these tensile stresses, you're removing one of these three main factors that cause stress corrosion cracking. And that's how laser peening was able to mitigate any failures in this type of testing for stress corrosion cracking. More industrial talks around this are for applications. Danny from Hepburn and Sons will be talking about laser peening for marine time. And that talk is 12:30 p.m. And here he's going to give an example of how laser peening is helping mitigate stress corrosion cracking for Navy applications. William from Entergy will be giving a talk at 1:25 Eastern Standard Time. And that one is going to show how laser peening is eliminating primary water stress corrosion cracking. So stress corrosion cracking in a nuclear environment. And also Professor Sano, as Alan explained, he worked and he was one of the original researchers of applying laser peening for nuclear reactors in Japan. Will be giving a talk today at 8 p.m. To explain how laser peening enhances, again, stress corrosion cracking in a nuclear environment. So moving on to the last slide, it's kind of my closing note, and the main focus here, I want to talk about how laser peening can be used to optimize future designs. So the larger number of customers that we get, the larger number of applications we get, are customers that have already problems in service. They have a component, it's experiencing one of the problems that I explained. So we need to go back and try to see how laser peening help improve the life of these components that are already in service. But a different approach that I've always advocated for, and we're seeing a lot of interest in, is actually using laser peening for future component design. A lot of the designers have the abilities now to do stress analysis and understand where their high stress locations that have predicted high intensity factors and so on. So they already have the ability to predict any failures that are going to happen in their part. And rather than complicating their manufacturing process or using a much more expensive alloy or using different techniques to generate the part, they're actually looking at laser peening process to enhance the part and only focus on the critical locations in that part, giving them much higher flexibility in their design, increasing their efficiency, allowing them to use lighter material or cheaper material, and still get the same performance that they're targeting and even a bit more. So this is kind of how I like to see the future, where we're predicting where a failure is going to happen and trying to mitigate it before it happens, or giving engineers in the field and designers the flexibility to use different materials, lighter materials, give them a higher flexibility to design things and push technology to the next level. So for the last slide here, this is the contact information for LSP Technologies. You guys have heard David Larman and Eric Collette, and I will leave this slide here for your reference, and I'll open the floor for your questions. So if there's any questions, please feel free to ask now.
Michael, thank you for your presentation. Appreciate the information you showed us. We do have two questions from the audience, and I'll read these. Both of them are from James Smith. The first question we have, this is pertaining to an image, a video that you had provided on the blade. It says, in the example showing the laser peening of the blade looked to be in the vertical position. And also, did I not see a plasma? And the second part of that question, was a water layer present? I think maybe just kind of prefacing a bit about what's going on in this particular video segment might help answer that question.
Yes, as I explained while I was showing this video, it's actually a demo of the laser peening process. I can't mute it right now. Maybe here. Let's see. There we go. So as I explained, this was actually just a demo to show the process. So in our processing, we go through initial step of verifying our robot programming. So that was this step. So actually, you're seeing the laser hitting the surface without any water. If you don't confine the plasma, you will have very small explosions happening. So it's just a demonstration. And the second video that I presented, it actually showed an actual laser peening process. And I'll get to that one. And then hopefully, it's a bit farther one to see, but you can see both of these features. We're generating a plasma through, you can see the water nozzle here, and I can zoom in. You can see the water dripping. That's how we're applying it. And since the laser peening is inside the hole, you can't actually see, but it's usually kind of a spark of light explosion generated from the plasma. I hope I answered that question.
I think you did. So basically what you're saying is that was a demo to really set up the blade to confirm processing and the area to be addressed, and it's a low energy setup for that particular configuration. And he had responded yes. The next question is also from James Smith. He says the plastic deformation generally causes microcracks. Do microcracks have a significant role in laser peening?
When we're laser peening, we do not see any microcracking. That's where the start of that thing. We're generating very low magnitudes of any cold work in the material. So the cold work in the material is a very localized near surface dimples, and I'm talking about few micrometers in depth. And the amount of cold work we're talking about, depending on how hard the material. For example, for these dies, I'm expecting like 1% cold work or maybe even less. So you're not damaging the material itself, but with using very low cold work in the process, you do not tend to see any micro cracking from the process itself. So we're not generating cracking, so we're not having the problems with the cracking itself. The only exception here is, and I mentioned it very quickly, is around titanium. And in titanium, because the plasma interacting with the material, if you don't put a protective layer, that could generate an alpha case, and the alpha case is very brittle, that has some micro cracking. And that's where you have reduced life improvement if you have alpha case during processing of titanium. I hope I answered that one too.
James, if you want to reply yes, that'd be great. Or if you think you've got another question to that, no, looks like he's agreeing to that. So